Hi, I'm Troy Hughes, developer and SAS author, and today I'll be sharing insights and methods from my latest book, SAS Data-Driven Development, and how these can be applied to help build LEGO gear trains. I'll show you how to leverage control tables and parameters to build software that is more flexible, reusable, and configurable, which benefits not only us software developers, but also those end users who rely on the software that we write. I'll demonstrate how data independence, a pillar of data-driven design, was essential in allowing me to create simultaneous SAS and Python versions of this software, both of which rely on the same underlying control tables and parameters. And because this topic can be somewhat abstract, I'll showcase all examples using LEGO gears and gear trains in action.
Have you ever had difficulty selecting LEGO gears, pairing gears with each other, or creating a gear train? Maybe you only wanted to transfer motion from one point to another within a LEGO model. Or in other cases, you may have had a specific rotational speed or torque that you were trying to achieve with a gear train. In this video, I'll be introducing many LEGO gears and demonstrating some best practices for gear selection to ensure you build the perfect simple gear train every time. I'll first define and demonstrate simple, compound, and epicyclic gear trains, of which only simple gear trains are the focus of this video. I'll next introduce several LEGO gears that can be used to construct simple gear trains, including spur gears, crown gears, double bevel gears, clutch gears, turntables, and differentials. I'll briefly discuss gear ratios, including how to gear up to increase speed or gear down to increase torque. I'll show how gear trains are manually designed, including tedious calculations for gear ratio, as well as the gap or overlap between two gears. But at the heart of this video is software I've created that allows builders to calculate how any two LEGO gears in a simple gear train will interact with each other, even at non-orthogonal angles. The output, which lists all possible simple gear trains, saves builders a tremendous amount of time and effort because they can evaluate gear trains virtually rather than having to waste time testing one gear combination after another to find the perfect match. Finally, I'll define and discuss data-driven software design and demonstrate why it was essential for this project, as well as how it promoted software flexibility, reusability, configurability, and interoperability. In a nutshell, data-driven design fosters higher quality software. And for anyone looking for additional information, including this SAS and Python code, a 69-page paper accompanies this video and is published on both the SAS.com and lexjansen.com websites. Importantly, this paper includes the comprehensive listing of LEGO gear trains that is referenced but not included in this video. Gear trains transfer motion and power from one gear to another. In some cases, this transfer of power is the only objective. You have a gear turning in one location, and you need that gear to supply power elsewhere, or possibly to apply that power in a new direction or even a new plane. Gear trains can additionally be used to increase gear speed or torque, which are inversely proportional to each other. But first, some basic gear nomenclature is required to distinguish driver, driven, and idle gears. The driver gear transfers power and is closest to the motor or power source. The driven gear, sometimes called the follower, receives power from the driver gear. Here, the large gray driver gear provides power to the smaller blue driven gear. Note that the gears rotate in opposite directions. If one or more additional gears sits between the driver and driven gears, these middle gears are known as idle gears or idler gears. Here, the idle gear in the middle may have been placed to enable the driver and driven gears to rotate in the same direction. Among other classifications, gear trains are often distinguished as being simple, compound, or epicyclic. A simple gear train comprises two or more gears interacting with each other in which each axle has only one gear. The previous examples have all demonstrated simple gear trains. However, simple gear trains are not always in line and can be constructed at right angles with bevel gears, double bevel gears, worm gears, or knob wheels. Here, a 36-tooth double bevel gear, the driver, turns a 28-tooth double bevel, the idle gear, which turns a second 28-tooth double bevel, the driven gear, at a 90-degree angle. This video focuses only on gear trains in which all gears are inline, that is, occurring in the same plane and having parallel axles. Compound gears have two or more gears rotating as a single unit on one axle. Compound gear trains contain one or more compound gears and are typically employed to increase either the speed or torque of the driven gear, in which case the size of the gears of the compound gear will differ. Here, a large Lego servomotor turns two 12-tooth double bevel gears, which in turn power two separate compound gears, and finally two 40-tooth spur gears that are attached to the lift arm. This arrangement of compound gears increases lift arm torque. However, each of the outer axles, despite having only a single gear size, is also a compound gear because two gears appear on each axle. Thus, both driver and driven gears can also be compound gears. For example, these two compound gears each comprise six 24-tooth spur gears turning in unison. The intent of the compound gear is not to modify speed or torque in this case, but rather to more evenly distribute torque across more gear teeth simultaneously. This provides greater strength and stability, but can increase friction substantially. Epicyclic gears, also known as planetary gears, are a third classification of gears in which the center of one gear revolves around the center of another gear. Epicyclic gears are not further discussed in this video. Gear ratio is the ratio of the number of teeth on the driven gear to the number of teeth on the driver gear. It can also be calculated as the ratio of the diameter of the driven gear to the diameter of the driver gear. In this simple gear train, a 40-tooth driver gear powers an 8-tooth driven gear, so the gear ratio is 8:40, which reduces to 1:5. In other words, the 8-tooth gear will make 5 revolutions, while the 40-tooth gear makes only 1, so the small gear will be turning 5 times faster than the larger gear. Anytime a larger gear powers a smaller gear, the gear ratio will be less than 1, which represents gearing up, in which the speed of the driven gear is faster than the speed of the driver gear. As this speed increases, the available torque inversely decreases. If a simple gear train cannot produce the required speed, a compound gear train can be utilized. For example, the largest and smallest Lego spur gears are 40 and 8 teeth, as shown here, so the simple gear train can only increase the driven gear speed by 500%. The Lego EV3 large servomotor has a maximum speed of approximately 210 RPMs, so a simple gear train with a 1:5 gear ratio can reach a maximum speed of approximately 1050 RPMs. So, if your Lego model requires 5000 RPMs, a compound gear train can achieve this. Here, the first axle turns at 200 RPMs, the second axle, a compound gear, at 1000 RPMs, and the third axle, a second compound gear, at the required 5000 RPMs. This clip shows the progression from 1250 to 2500 to 3750 to 5000 RPMs. Now in slow motion, you can see the driver gear turning at 50 RPMs, the center compound gear at 250 RPMs, and the driven gear at 1250 RPMs. Gearing down occurs when a smaller gear drives a larger gear, in which case the gear ratio will be greater than 1. Gearing down reduces speed while increasing torque through mechanical advantage. In this simple gear train, the two gears have been reversed, and the 8-tooth driver gear now powers the 40-tooth driven gear. This produces a gear ratio of 5:1 and a mechanical advantage of 5. In other words, the driver gear will turn 5 times faster than the driven gear, but the driven gear will have approximately 5 times more torque and the ability to rotate, lift, or otherwise move greater mass than the driver gear. If sufficient torque cannot be achieved through a simple gear train, a compound gear train can be utilized. This compound gear train has a gear ratio of 28:12, 40:8, and 40:8. so the cumulative gear ratio is 58 1/3 to 1. Note that as speed and torque are inversely proportional, the 40-tooth compound gear connected to the lift arm moves exceedingly slow as compared to the driver gear on the servo motor. This is the cost of torque, and why LEGO models that move heavy loads are often shown as time-lapse videos, because they take forever to complete their tasks. A touch sensor in this model is activated when the lift arm reaches the horizontal plane, at which point the servo motor pauses for a second, after which it reverses direction to raise the lift arm. However, because excessive torque can damage gears or dislodge models, your design always should accommodate for the anticipated increased torque. For example, I've now disconnected the touch sensor so the EV3 brick won't know when the lift arm is horizontal. Rather than pausing and reversing, the servo motor now continues, forcing the crane from its perch and stripping a couple 8-tooth spur gears in the process. Runaway torque such as this should be avoided because it can damage LEGO gears and worse, LEGO servo motors. No gear train, whether simple or compound, is ever 100% efficient, so some torque and power will always be lost. But where gears mesh well, in which the gap or overlap between two gears is minimized, gear train efficiency will be maximized. For this reason, goodness of fit between gears should always be evaluated, and can be calculated for all gears in a simple gear train. Only simple gears are discussed in the remainder of this video. Designing a simple gear train begins with a selection of gears that will mesh well with each other. Of course, simple gear trains can contain more than just two gears. However, each additional gear still represents only a one-to-one pairing between two neighboring gears. So for this reason, the gear trains examined will include only two gears. This video highlights only LEGO spur and double bevel gears. However, a comprehensive list of all LEGO gears, past and present, is provided in the referenced white paper, Data-Driven Robotics. It includes photographs and metadata for 41 LEGO gears, including gear versions where LEGO gear design has evolved over the years to strengthen components. It also includes links to each gear on the bricklink.com website, without whose exhaustive LEGO database these gear metadata could not have been compiled. LEGO spur gears are the OG LEGO gears, dating back to the late 1970s. Both the 8-tooth and 24-tooth spur gears have been improved over the years, with the current version of each pictured to the right. Note that each 24-tooth gear covers 3 holes, or studs, and each 8-tooth gear covers 1 hole, or stud. Each LEGO stud represents a distance of 8 millimeters, so a LEGO gear's diameter in millimeters will always equal the number of teeth. For all LEGO spur gears, the number of teeth is divisible by 8, so any spur gear can mesh with itself at orthogonal angles. Here, 2 24-tooth spur gears mesh horizontally, and 2 8-tooth spur gears mesh vertically. Only the 60-tooth LEGO turntable has both spur teeth and a number of teeth not divisible by 8, although turntables are not discussed in this video. Double bevel gears are so named because they can mesh inline, at 90 degrees or at intervening angles, so long as they can be reliably attached to underlying LEGO beams. Double bevel gears are relative newcomers to the LEGO world, having been introduced in 1999, more than 2 decades after LEGO spur gears. In 2019, and with much fanfare, LEGO debuted the 28-tooth double bevel gear. Unlike LEGO spur gears, LEGO double bevel gears cannot be paired with gears of the same diameter. This is because their number of teeth is not divisible by 8. This social distancing is observed on the left, with 2 12-tooth gears unable to touch, and 2 28-tooth gears unable to touch. To the right, the entire family of double bevel gears is demonstrated, including the 12, 20, 28, and 36-tooth gears. Again, for reference, spur gears can touch themselves, whereas double bevel gears cannot. This can make the design of double bevel gear trains less straightforward, and in part spurred my interest in designing software to overcome this challenge. Designing gear trains at non-orthogonal angles, in which the angle between gear axles is not in line with or 90 degrees to the underlying Lego beam, can often yield uncommon yet useful gear pairings. To facilitate this quest for non-orthogonal gear trains, a 9x9 stud matrix can be constructed from 9 Lego beams, in which the upper left position will be designated as the driver gear. For example, this 16-tooth spur gear powers a 20-tooth double bevel gear, in which the 20-tooth gear is positioned 2 studs to the right and 1 stud down from the driver gear. Or, if you wanted to create a gear train in which a 24-tooth spur gear powered a 20-tooth double bevel gear, the 20-tooth gear could be positioned 2 studs to the right and 2 studs down from the driver gear. Finally, if you wanted to create a gear train in which a 20-tooth double bevel gear powered a 36-tooth double bevel gear, the 36-tooth gear could be positioned 3 studs to the right and 2 studs down from the driver gear. But wait, the gears sort of mesh, but there seems to be a substantial gap between the teeth, more than usual at least. And upon closer inspection, it is apparent that the gears can be pried apart rather easily. So this gear train might not be a good candidate for high torque applications, because the gears might slip. Thus, non-orthogonal gear trains can be especially useful. But they are uncommon in part because they are often encountered through trial and error, and because the gap or overlap between the gears might need to be calculated to determine their goodness of fit, the degree to which they mesh well with each other. And this calculation requires comparing the sum of the radius of both gears to the hypotenuse created by the rise and run of the number of studs between the axle holes. In other words, this needlessly tedious process needed to be automated, and data-driven software design provided the most effective and efficient solution. Data-driven design can be defined as software design in which the control logic, program flow, business rules, data models, data mappings, and other dynamic and configurable elements are abstracted to control data that are interpreted by rather than contained within code. Data-driven design is contrasted with less favorable hard-coded or concrete software design, in which changes to software functionality require modification of the code itself. In the next few minutes, I'll demonstrate how data-driven design underpins Lego gear train analysis in this software. For example, the table of gear attributes is the primary source of control data in this software. All calculations for gear pairing goodness of fit are derived from this table. This design facilitates software flexibility and configurability because end users can maintain their own individualized tables of gears. One Lego builder lacking some gears might choose to remove specific records from the table so that only available gears would be evaluated by the software. Yet another user, a savvy engineer with a 3D printer, could design and cast non-standard gears that were compatible with Lego gears, and could include these customized gears in gear train evaluation by adding them to the control table. Neither modification requires any update to the code, only to the control data. And this is the beauty of data-driven design. A second control table comprises pairs of comma-delimited XY coordinates that reference Lego studs, the holes into which Lego axles could be positioned for use in gear trains. XY coordinates are expressed in millimeters from the source of some starting position, such as the upper left stud. This table shows the 9x9 matrix of Lego beams previously demonstrated. The gear train software also defines and utilizes several parameters, another type of control data and hallmark of data-driven design. For example, the fuzz parameter allows the user to specify the acceptable gap or overlap in millimeters that will be tolerated in theoretical gear trains, thus eliminating results that lack goodness of fit. A final facet of data-driven design worth mentioning here is data independence, which promotes software interoperability. Because the gear attributes and XY coordinates are maintained in separate control tables and not as hard-coded logic within program files, these control tables can be leveraged by other software applications and programming languages, such as the equivalent Python demonstrated here. The parameters are also identical in both the SAS and Python instances of the software, allowing one set of program documentation to suffice for both software applications. So now that you've had a brief introduction to data-driven design, I'm excited to show you how those concepts and methods can be utilized within gear train analysis. So the first thing I've done here is open up the PDF. Again, this is located on both the SAS.com and LexJansen.com websites. You can see a number of gears that are pictured here, but more important than the pictures are the metadata behind them. And those metadata are contained within the gears.csv. It's a comma separated values file, and this can be opened in Excel or your favorite application. CSV files and other canonical file formats are highly preferred in data-driven design because of their ease of data transferability. For example, this control table was designed to be accessed not only by SAS but also by Python. For this reason, it would be impractical to save these data as a SAS dataset, as we would commonly do in the SAS ecosystem. Continuing to scroll down the PDF, you'll see a reference to Appendix A, which is the Lego Gear Combination SAS program file. We can open up this file within the SAS Display Manager and find that it contains 4 macros. The first gear report we just ran, which generates the HTML formatted report of gears and gear attributes. That's very useful. The second macro, create rectangle, creates a matrix of beam positions, so those XY coordinates that demonstrate the axle holes into which gears can be placed to create those virtual gear trains. The third and fourth macros, gear train report and eval chords, are the 2 macros that perform the goodness of fit calculations. A second SAS program file is also contained within the PDF, and this file ingests and invokes the first 4 macros. So after opening it up, I'm going to go up here and change that default file location. I've previously been using the SAS University Edition, so I'm going to change this to my local D drive to ensure that the files accurately run. After this modification has been made, I can highlight the text, run the file, and presto, here's the HTML formatted report, courtesy of the SAS proc report. Opening this up, you can see this is the report that was also produced in the PDF, and clicking on any of the dynamic URLs will take you to the Bricklink site. This is very beneficial if you're looking for additional information about gears, or if you're trying to purchase some of these Lego gears for yourself. And while I'm on this site, I'm going to do a little bit of research. I recently heard a rumor that the Lego Group had released a new gear, a 28-tooth double bevel gear, something that I don't have. And when I type in the search engine, I find that in fact there are 2, a gray released in 2019 and a red released just recently in 2020. So of course I need to purchase these, but something else, I need to add these data to my control table. With the Gears CSV file open, I can now make these modifications and add these 2 new Lego gears to my control table. This will be extremely beneficial because while I'm waiting for the parts that I've just ordered online, I can start designing theoretical gear trains even before I have those gears in hand. As I'm making these modifications, you can see that I'm pulling the metadata directly from the bricklink.com website. For example, every Lego piece has a unique part number. It's important that this number is transcribed correctly because it's also required in the URL. So the dynamic links in the SAS report will not work unless the part number is correct. Something to note about the date, although this is a new gear, the date is listed only as 2019. This doesn't necessarily mean that the gear was stopped production in 2019. However, it may mean that no new sets have been produced yet in 2020 that incorporate this gear. Once the control table has been updated with the 2 new gears, the only thing left to do is to rerun the software. Again, we're not having to make any modifications to the underlying code because the software will automatically recognize that the control table has been updated and incorporate these new data. So looking at the original report that was produced, you can see that there are 28-tooth gears, but not the 2 new gears, just differentials that existed prior to 2019. So in rerunning this software, now as we refresh this HTML output, you can see that the 2 28-tooth double bevel gears have now been incorporated into the report, and again without the need to change any of the underlying software. Before you exit, you might want to click on these links just to ensure that they are valid, and it looks like both 28-tooth gear links are working, so we can close down this report and continue running software. I had mentioned that there were 2 principal control tables in this software, the first being the Gears CSV file, which contains gear attributes, and the second being the table of beam positions, which contains XY coordinates for each of the axle holes into which gears can ultimately be placed. The next step is to run the create rectangle macro, which creates a matrix of XY coordinates representing the positions into which LEGO axles can be placed. The macro has parameters that allow the user to specify both the height and width of the matrix produced. In this example, a 9x9 matrix contains 81 possible holes into which axles can be placed for gear train calculation. With the gears control table now updated and the 9x9 matrix of axle hole positions created, the next step is to calculate theoretical gear trains. The eval chords macro has a number of parameters as listed in the accompanying white paper. For example, setting verbosity equal to verbose specifies that each gear will be listed uniquely in the output. If verbosity instead is set to brief, then each gear will be aggregated into groups based on the number of teeth. And as mentioned previously, setting the fuzz parameter to 1 specifies that any gap or overlap will be less than 1 millimeter. With verbose on, gears are listed not only by the number of teeth, but also by the type of gear, the type of axle, and if relevant, a version number. For example, 24-tooth gears comprise spur gears, crown gears, and a differential gear. More concise output can be achieved by changing the verbosity parameter to brief. Note that in this data-driven design paradigm, only the parameter must be changed, not any of the underlying code that rests within the SAS macro. Note that in the updated results, only one 24-tooth gear is now listed, irrespective of the type of gear, type of axle, or version if it exists. In general, using the brief setting is preferred because it creates much more readable output. To conclude, let's revisit the 3 gear trains we created manually and demonstrate how a programmatic data-driven approach is much more efficient. The first gear train was a 16-tooth spur gear powering a 20-tooth double bevel gear. It turns out, according to this HTML formatted output report, that this had a 0.111 mm overlap and a 1.25 to 1 gear ratio. The second gear train was a 24-tooth spur gear powering a 20-tooth double bevel gear. This had a 0.627 mm gap and a 1 to 1.2 gear ratio. Finally, there was that infamous third gear train that really didn't fit because of the gap. This was a 20-tooth double bevel gear powering a 36-tooth bevel gear, and this had a 0.844 mm gap and a 1.8 to 1 gear ratio. And because we now know that a gear train with this substantial a gap is unacceptable, we can modify the fuzz parameter from 1 mm to 0.8 mm, run the software, and produce more optimized output for further gear train evaluation. All without modifying code thanks to data-driven design. It looks like my new 28-tooth double bevel gears have arrived, so it's time to go build. Of note, a friend recently asked, how long did it take to put together this presentation? To which I replied, I've been working on it since the 3rd grade, when in fact I gave a talk at a local science fair entitled Gears in Action, showcasing LEGO gear trains. I hope you've enjoyed this foray into LEGO robotics and gear train analysis, facilitated by data-driven design, and thank you for watching.